How was real analysis midterm? Those who are in real analysis. It's a real question. All right, fine. Don't talk to me then. Okay, so last class I was like delirious, so that may have been a little confusing, and also there was some real Overheard at Yale content there that I hope did not end up on Overheard at Yale. I guess you all don't really use Facebook anymore, so maybe that is a redundant group. Please do not post anything I say to Overheard at Yale. I quite enjoy my job for the moment. Okay, so what we were talking about last time was equivalence relations and partitions. Oh wait, before I start doing review, we have a midterm next Thursday. Not this Thursday, next Thursday, in class. Okay, remember? I know you all know. Those people, they might not know. Rosa is running a review session hour this week. We also have our new ULA Journ, and then there's all my office hours. And I won't give you a homework due next week. So you can just focus on your midterm instead. Okay? All right, so anyway, partitions and equivalence relations, that's what we were talking about. So a partition, intuitively, is just a way of dividing a set up into pieces. That's all. So if we think of our set as being like the blob, then we can divide it into a number of pieces, right? There you go. That's a partition. So formally speaking, a partition is a collection of subsets of our set. So it's a subset of the power set. So that every element of our original A is in exactly one of the pieces of the partition. And then also, we don't want the empty set to be a piece. Yes?
Should it say with x and pi?
Probably. X and pi with A in it, yes. Thank you. Yeah, so if pi is our partition, it's our collection of pieces. Every little a and big A is in exactly one of the pieces, right, which is the x in pi. So each x, let's follow through the logic, right, each x in pi, because pi is a subset of the power set, right, x is in the power set of A, so x is necessarily a subset, just from the way we set things up. Okay, so this is one way of slickly writing what I said intuitively up here. And yeah, which is the bonus condition, we don't want the empty set to be in the partition. Okay, and then dually, there's this thing called an equivalence relation. Now, equivalence relations are usually denoted with this little tilde symbol, like in between things. So we'd write like A tilde B to mean like A is related to B. So we write it in flex notation. I'll start using that today. I used R last time for relation, but equivalence relations are usually this, or other things that look a bit like the equal sign, okay? Because equivalence relations are kind of like equals. So an equivalence relation is a binary relation which is reflexive, symmetric, and transitive. So reflexive means everything is related to itself. Symmetric means you can turn everything around, right? If A is related to B, B is related to A. And transitive means if A is related to B, is related to C, then A is directly related to C. So you can take big steps. This is a second meaning of the word transitive. I introduced one in the homework a while ago. This is a different usage of that word. This is very unfortunate, but both of these words are very standard, and so we just have to live with it. So when I say transitive relation, I mean this version, right? If A is related to B is related to C, then A is related to C. If I say transitive set, then I mean what I said on the homework, which is that every element is a subset. There's some tiny bit related, right? If you think of sets, living in sets, like as a relation, right? The relation of being in Them being like a transitive set and a transitive relation. You can think about like the things that are in your elements are in you. So everything 2 steps away is only 1 step away, which is kind of like this, but not really. Okay, and the thing about partitions and equivalence relations is they're actually kind of the same. Each partition determines an equivalence relation. Each equivalence relation determines a partition via the equivalence class construction. Is that good so far? I'm impressed there's so many of you here today. It's raining slightly. Hello. Is its own equivalence class. Yes. The equivalence relation is determined by pi itself, like it by all the pieces. Okay. So, and then so among all of the inappropriate content last week, some people thought that was hilarious. Some people are probably like, could have been math. I drew a picture, and then I talked about something else as if that picture was still pertinent, and it wasn't, and I didn't draw the new picture. So let me start there, which is here on the handout, and hopefully explain a little better what was happening. Okay, so let's suppose we've got our set A, which we've partitioned up somehow. Okay, so we've got A, and then I've got another copy of A below, but I'm thinking about it as partitioned here. Okay? And then let's suppose I have another set over here, B. Okay, so this is A. We could either say this is a partition of A, or we could say this is A mod an equivalence relation. Right, those are the same. If you look back at your notes. Okay, so there's something called the natural projection map from A to the partition. Right, and what it says is, on input little a, give me where A lives in the partition. Right, so this is the natural projection. Did I denote it phi last time? I think I probably did. I didn't give it a name. It's often called phi. So phi of A is the equivalence class of A. And we have notation for that, right? It's the square brackets again. Always with the square brackets in this class. Okay. So we always have this whenever we have a partition. We can send an element to the piece of the partition that it's in. Okay. So now let's suppose we have a function this way, a function. So the picture I drew last time was about this one here, and it was asking, under what conditions does a function here exist so that going from A to B is the same as going from A to the quotient and then to B. So I want every path along the arrows to be the same. Okay, so when does there exist G from the quotient to B such that, let me get my compositions right, F is equal to G composed phi. Does this question make sense? Don't take that one. Take that one. Okay, so the key idea here is that if two things up here are in the same piece down here, then their value on F had better be the same. Right? So if A and A prime are in the same thing down here, then the value of this mystery function on that piece has to be the same. Okay, so the answer is when basically things that are related get mapped to the same thing by f. When f of little a equals f of little a prime for all equivalent a and a prime. Okay? So it's literally just saying that like f doesn't send different things in the same piece of the partition to different things in B, right? So sometimes we would say like f is congruent for the equivalence relation, right? It respects the equivalence relation. What's a good example of this? It would be really helpful if everybody had already taken a topology class, but they haven't. So I guess, okay, so take A to be the natural numbers. And B to be the set 0, 1, 2. What we're going to do is we're going to map a natural number to its remainder on division by 3. Okay, so like 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 0, right? Because 3 is exactly divisible by 3. 4 gets mapped to 1, 5 gets mapped to 2, 6 gets mapped to 0 because it's divisible by 3. So f is, if it equals remainder and then, so if you like your fancy notation, this is n mod 3. You've seen that before. Right? It's just n mod 3. Okay, now, what quotient am I going to use? Let's try, firstly, let's glue together all numbers which have the same remainder on division by 3. We used this example last time, right? So like 0 and 3 and 6 and 9 and 12 and 15, those are in one equivalence class, right? And then 1 and 4 and 7 and 10 and 13 and so on are in another, and whatever is left is in a third. All right, so then you could take this is oh well. Seven. Oh no, I'm running out of space. 5, 8. People on airplanes always expect me to be really good at arithmetic when they like learn what my job is, and they should watch this where I try and add 1 to 7 and flounder. Okay, so in this situation, this function works out, right? There is a function from the quotient over here. Because if two numbers up here have the same remainder on division by 3, for instance, 7 and 10, right? They're both mapped to 1, but they're also in the same equivalence class down here. Right? So things that have the same equivalence class are related. All right, so this example works out, right? There is a function g that goes this way. And that's perhaps like not especially surprising because everything's here about division mod 3. Yes, Rudy, what's up?
On your bottom left sketch, but that one just had
Just 3 pieces, exactly. Yeah. All right, so this one works out if you work through all the details, right? There is a function from the quotient to here. That function is taking the piece of the partition and spit out the smallest number. Yes? That is a slash tilde, yes, that is the quotient. All right, so now this is an example where it all works out. All right, so we have a function. Okay, so now let's fuss with it a bit and see if we can break it to understand it a bit better. Okay, so we're going to only change this example ever so slightly. So now let's let f be the map division on remainder 6. Not 3, 6. Okay? So 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 0. 7 goes to 1, all right, and so on. This, still the same. Is there a function from here to here? So if two things have the same remainder when you divide them by 6, is it true that they would live in the same equivalence class down here? Yes, right? It still works. Right? Because 1 is related to 7 and 13 and 19, and those are all in this equivalence class. Right? And 1 is not related to 4 up here, but it's okay, because 4 is related to 10 and 16 and 22, and those are all in the same equivalence class. All right, so if you change this map to be mod 6 instead of mod 3, we're still okay, even if we don't change this map. Now let's do it the other way around. So f is division on remainder 3. This now is I'm going to group things by remainder on 6. So I now have 6 pieces in my quotient. So 0 is now related. 0 lives in the same thing as 6 and 12 and 18. It does not live in the same thing as 3. Yes, what's that? They do.
Like 0 and 3 are in the same position, but they go to different things constant.
Did I do my things the wrong way around? Maybe. It works one way but not the other.
You have more elements in the like result states than you have provisions.
That's not true.
Oh, I guess if you don't need every element.
It doesn't need to be injective.
Yeah, I take that back, but I still think
Oh, this is what happens when I do things spontaneously. Shall I write out the details or should we move on? How are we feeling? Is it worth working through this example for y'all? Or are we okay in general with this? I was like, let's just throw this out there and hopefully it'll work the first time. And I'm hearing some dissent. I forgot that none of you have any opinions. So it's hard for me to... Okay, so I mean, you can think, okay. Let me do the perfect solution to this. If you are interested, work this out yourself. All right, so think the function that takes a number and returns its remainder on division by 6. Can I do this with it? Can I first stick everything together in mod 3 and then map over? Yes? It's, for the example that works, this thing goes to 0, this thing goes to 1, this thing goes to 2. Yeah.
Is that for where f is mod 3 or mod 6?
Where both things are mod 3. Yeah, so you can think of the combination where like this is mod 6, this is mod 3, and the other way around. One of them works and the other doesn't. And I can't remember which one's which. It's to do with which one's coarser or finer. I'll think about it in the break and then I'll get back to you. All right. Anyway, I wanted to move past this anyway because we were talking about other things. So this, we have our function from a to b, and we're interested, can I have a function from the quotient to b? But it turns out what happens more often is we have a function from a to itself, and we want to know if there's a function from the quotient to itself. And that's what we were investigating last week with a like 2 times n, n squared, and 2 to the n example. Okay, so the picture there, woo! Let's get rid of this. Okay, yeah, you're right. The other way works. If this is division on remainder 6, then 4 goes to 4, right? But 4 here goes to 1. Or 1 goes to 4, right? Something has to break. Other way around is fine, though. All right, so more common thing. Okay, so here, this is, let's have A again, and we'll have another copy of A, and we've got a function, f. Okay, and then we have our quotient, which I'll only ban the bomb. Okay, so this is our setup. All right, so we've got a function from a to itself, and I'm not going to draw an arrow to myself because that's confusing. I'm going to take another copy of a and have this function. Okay, and then we've got 2 copies of the quotient down here. And so the question is there a function, let's call it g, mystery function, so that if I start in A and then go down and then go over, it's the same as starting in A, going over, and then going down. Okay? The question is there a g such that compositions, let's get it right. Phi composed G is equal to F composed, oh for goodness sake, sorry y'all. Right, so the one on the left, you read functions right to left, right? So this is f first, then projection. This is projection first, then g. Okay. So the question is, when would such a g exist, or when would it not exist? Right, and we investigated some examples of like some particular examples to like see when it works and when it doesn't work. So if you recall, and I do want to do this again because it is important and I was losing my mind. The examples was n is a, so you're taking the natural numbers again, and our function is our quotient is n mod 6, meaning 2 things are equivalent if they have the same remainder on division by 6. So n is equivalent to m if and only if n minus m is divisible by 6. It's another way of saying modular arithmetic, okay? So 0 and 6 and 12 and 18 are related, and 1 and 7 and 13 and 19 are related, and so on. Oopsie. So if you wanted, you could write out the equivalence classes at the bottom, right? We've got 0, 6, so on, 1, 7, so on, right? And this keeps going. And people who complained about the screen being in the way, I apologize to you specifically. Also just move to a different chair. In fact, I retract my apology. I'm perfect. So this is the projection map. So the projection map, right, it takes like 12 and it maps you into like this set here, right? And it takes 13, and it maps you into this set here. So, and that's our projection. Okay, so our first f was multiply by 2. And the question is multiplying by 2 then going down to the quotient by the projection the same as going down to the projection first and then trying to go over? Or I guess not just that, like is that even possible, right? Because I haven't even told you how you go over yet. So what would our function g do? So it wants to take an equivalence class and give you another equivalence class that like is a bit like doubling. So for instance, here's an equivalence class. 2, 8, 14, 20. Where should G send this thing so that this is true? Yeah, right? Equivalence class of 4. Why 4? Because that's double 2. Right? So starting at 2 and going down, I end up here. So wherever I end up has to be where if I go this way. But 2 goes to 4. Right? And then goes down into the quotient. So just because of what f does to 2, this equivalence class must go to the equivalence class of 4. I can add 6. There you go, proof. Does that make sense? Question is, does that work, right? So the way we worked that out was saying, okay, where does 2 go? But this has to work for everything over here. So if we, right, 8 goes down into the equivalence class of 2, goes over to here. But if we go the other way, what happens? 8 goes to 16. Where does 16 go? Well, it goes to the equivalence class of 16, right? But that's the same as the equivalence class of 4. Look, they're in the same thing. So the idea is, if two things were equivalent before, they are equivalent after. That's the key observation that makes this work, right? 14, if we double it, it goes to what, 28? And 28 does live in here, because it's 4 more than 24, which is divisible by 6. All right, and you could keep going. Okay, so this works whenever equivalence before and applying f is preserved by f. Yes?
Then with like the g function down there, because you're preserving essentially all the same equivalence classes, they're just shifting exactly which one it is.
Yeah.
So does the g function literally just like mirror all the equivalence classes across?
It doesn't. I don't know exactly what you mean by mirror, right? It's not the identity, because these aren't the same. But you make your 6 equivalence classes here, you make your 6 equivalence classes here, and you've just got some arrows going around them. Yeah. It's not an injection, though, because like the equivalence class of 3 goes to the equivalence class of 0, right? Because double 3 is 6. But so does the equivalence class of 0. Okay, so this works. Okay, I mean, we showed it worked for this equivalence class, right? It works for the rest too. Works because if n was equivalent to m, then f of n was equivalent to f of n. Okay? So this is the condition we need for this to work, right? We need given an equivalence class, I need it to not matter which element I chose to evaluate f on, right? Which means they should all be, all their values should be equivalent as well. Okay, so this works in this case, right? And you can actually like prove that using arithmetic. It also works for n squared, using difference between square argument. It does not work for 2 to the n because you can find numbers which are equivalent mod 6, but where 2 to those numbers is not equivalent mod 6. All right, so this is where we got the end last time. Does this clarify all of the, yeah, good. I can tell when I'm doing a bad job, I just can't fix it live. I can fix it the next class, though, after I've slept. All right, so this is a formal version of the observation we just made, written in slightly different language, right? I'm using R instead of tilde. Okay, does anybody, this feels like a theorem that we shouldn't prove. How do we feel about that? Yeah? Okay, you're like, whatever. If you, like, this example, generalize it, and that's the proof. So the details of saying, like, what would it mean for there to be this function? Well, it means that I need things that started equivalent in A to end equivalent in A after I apply F, and then I can define something on the quotient. Okay, this is a surprisingly helpful thing in topology and algebra. Okay, scroll down. Oh. And I want to make an observation about equivalence relations. Well, that's just made things worse, hasn't it? Oh, just so you all know, I've decorated my office for Halloween, so you should come by and see. It's pretty good. I'm the only one in the math department who likes fun. No one else decorates for Halloween. I've been trying to get everybody to dress up for years. No one does it. They suck. I hate them. Okay. If you all want to do a group costume, 270 costume, that would be sweet. We'd have to wear it on the 1st, I guess, because Halloween's a Monday. Terrible. You know what's funny about being an instructor, actually, is on Halloween? You have to like leave campus as early as possible before people change into their second costume that they plan to wear for parties. Because like, I don't want to see that. Like, I don't want to see it. Students don't want me to see it. So I need to leave by like 3. Right? So people can get ready and enjoy themselves. Okay. Okay, so discussion at the end. So when we're doing this, it's much easier to talk about like what we do to 2 than what we do to the equivalence class of 2, right? It's just easier linguistically, right? Because there's fewer words, and it's easier to reason about it. So there's a formalized way of talking about that, which is that we select a representative from each equivalence class. So each equivalence class gets a guy, and that's going to be the one who's representing it. And often when we're doing modular arithmetic, you choose the smallest element, right? So 4 is the representative for the equivalence class of 4, because it's the smallest one. Excuse me. But the representative for the equivalence class of 11 is 5, right? Because 5 and 11 are related, mod 6, and 5 is the smallest such thing. Okay, so, and often like we use our representatives to define functions, right? We select a representative and we define a function, and it works. It's this operation we're doing. Okay, so this is a very natural thing to do, and it happens a lot in practice. And so we might wonder, okay, can this selecting representative things, can I prove in my set theory that we can always do it? And the answer to that question is no, without the axiom of choice. So for this equivalence relation here, we can select a representative because we've got a nice rule for it, right? Which is pick the smallest one. That's a nice rule, right? But if you have an equivalence relation on a very badly behaved set, which has no structure that you can exploit, and the equivalence relation is very bad, it has no structure you can exploit, then it seems like there might not be a rule by which to pick the representatives, which means we're going to have to make a bunch of arbitrary choices. And that's the axiom of choice kicking in again. So the statement, every equivalence relation has a unique set of representatives, is actually equivalent to the axiom of choice. It's another one. So I gave you a homework question about this, right? That's probably quite hard. I just thought of that one while I was writing it, and that's always a sign that it's going to be hard. So we've got what, like, if there's a surjection one way, there's a inverse, right? That's one statement of the axiom of choice. Second is a product of non-empty sets is non-empty, right? That was our second version of the axiom of choice. This is a third version. And none of those are the usual version of the axiom of choice, but they are all equivalent. Okay, how are we doing on time? Is it a good break time? Oh, it's excellent break time. Let's have a break. And during the break, come pick up the new handout. There hasn't? For real? Yeah. It might be on Gradescope, and then I forgot to put it on Canvas. It's been on Gradescope since Friday. Yeah. Oh, damn it. If I did that, then I need to give you all an extension till like next week. No. What's that? This is new. Do you want one from last week? Yeah, go nuts.
James, can you also post a LaTeX code?
Yes, I forgot. That I did forget to do, but the tech code? Yeah. They're all in the same place as the first one. So if you go to the announcement for the first one, and let's have a look. In fact, why am I projecting my voice? Let's turn that off.
It's kind of hard to listen. Like that was and then I that's what he said. Horribly. I like this picture. What? I found that
That code gets more and more complicated because I had to use
Yes, I was looking
If you're jumping in now, you might have a bad time. Oh, then you're fine. All right.
Apparently I forgot to put the homework on Canvas, so, you know, there's one of those extensions where just send me it, like most of you do anyway, late. Exploiting my kindness. Yeah. Blah, 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 blah. You want to have a handout? That's my one. You can't have it. That's old. This is new. What's up? Sure. Oh, so yeah, they're just different. If I've got A and B and I want them both living in A, I'll often use A prime, A double prime instead of. Yeah, it's a new symbol. Instead of subscripts, I'm using primes. That's all, yeah. It's not like the derivative or anything. It's not an operation. Get out of here. What do we got? Natural numbers. Is anyone a senior? Are y'all feeling that the dining halls have been a bit of a letdown this semester? That's the consensus among... No? Oh, okay. Okay, so the...
Or the variety or the
I think the quality is fine, but the dessert selection has been severely limited. We used to get those cheesecake brownies, which are the best thing I've ever eaten. In my, people are remembering, the cheesecake brownies. And we used to get macaroons on Fridays sometimes. Yeah, exactly, coconut macaroons. And now, if we're lucky, we get a cookie. And also, Franklin used to just like bring out more dessert, even like 5 minutes before the door closes. Now, if it's done, you're out. You lose it. So. Yeah. Yeah, they don't have it anymore, right? That little, the mezzanine. Yeah, that's disappeared. My sweet Franklin. What's it? It used to be Franklin. And I will always love Franklin the best, but c'est la vie. Everything gets worse. I think there's a law of thermodynamics to that effect. Okay. Also having chicken fingers every week. Didn't they have it? Oh, okay. And none of them are open late anymore. They used to be open late, people who are new. I mean, at lunch. The one I use. Talk about me here and my needs. Okay. Let's build the natural numbers, team. Let's build the natural numbers. So we've been fussing about a bunch with building lots of objects which you already know about, like functions, and then some objects that maybe you haven't seen before, like relations. But we've been deep in the mines of mathematics, so let's build something a little more mathy. So, in fact, our sort of mathematical goal for a little while is to build most of the number systems you're familiar with. So we're going to build the natural numbers. Let's lose the microphone. Did I just whack? No, we're good. Natural numbers, and then we'll build the integers out of those, and then we'll build the rationals out of those, and then we'll build the reals out of those, and then I'm not going to build the complex numbers because I don't care. Yeah, take that, complex analysis. But like these are things you can do, right? You can build more complicated number systems out of simpler number systems. But doing so axiomatically is a little bit tricky because you have to work out what is it about the natural numbers that makes them the natural numbers compared to the integers. Right? Using some language I haven't actually introduced yet, they're both countable. So it's not just the size of the sets which are important, it's some other stuff that's important. And what's important about them is how plus and times and the order relation work on them, as we'll see. So that's a summary of that wall of text there that you can now ignore. if you'd like. One more thing before we build the natural numbers is I need to tell you what an order is. Whee! Okay, so why do we care about this? Because one way to distinguish number systems from each other is how the order looks. So for instance, the natural numbers, from an order perspective, looks like this, right? Whereas the integers looks like this. Right, it's infinite in both directions. And that's not like a deep observation, but let's develop some language to talk about this formally. Okay, so we're doing linear order? Yes, I am. So a linear order, that's not how you spell that word, on A is a relation satisfying. Okay. So there are a few different ways to axiomatize this. The shortest is the way the book does, which is not the most common way, but we'll go with the book. So number one is the relation needs to be transitive. It's a relation less than. I'm doing strict less than here, just in case. You can also do non-strict less than, right? You can do less than or equals, and you have slightly different axioms. And then you prove slightly different theorems, but it's all the same. And then 2 is that less than satisfies trichotomy. Is that an E or an O? Oh. Which I think means 3 parts. Trichotomy. And I have to tell you what I mean by this. So what I mean is, for each x and y, exactly one of the following holds. So either x is less than y, or x equals y. What am I doing? X equals y, or y is less than x. Okay. So for us, a linear order is a relation that satisfies this. This is sometimes called a strict linear order, because I don't allow less than or equals, and you can have the non-strict version where you allow equals. Okay, so let's make some observations. Yes, question earlier.
Sorry, I misread that.
Okay, good. Okay, so proposition of. Okay, so here's a question for you all. According to this definition, can something be less than itself? I've got some no's. People who are saying no, why not? Yes, right, it'll be less than itself and equal to itself, which is 2 of the following, which is not allowed. Okay, so proposition. X is not less than x. Right, because if x equals x, then by exactly one of the following, I can't have either of the comparisons, even though they're the same comparison. Okay, and then the second, and this one's harder to state. So if two things are different, not the same, then then one of them is smaller. Okay? That also follows from trichotomy, right? If things are not equal, then this does not hold, so one of the comparisons must hold. Here's a question. Can both of the comparisons hold? Could x be less than y and y is less than x? No, again by exactly 1, right? Exactly 1. Also, if x is less than y and y is less than x and we're transitive, then x is less than itself, which we know is false. That's another reason. So this is exclusive OR here. So this property is sometimes called irreflexivity of the relation, right? Nothing is related to itself. It's like the opposite of reflexive. Irreflexive. And this one is sometimes called connectedness, right? I can get from anywhere to anywhere else via the relation, maybe by going backwards. Okay, and it is a theorem of of order theory. The trichotomy is the same as being reflexive and connected. These are actually equivalent. So usually books define a linear order as a transitive, irreflexive, connected relation. And then they prove trichotomy. Our book does the other way around, which is it takes trichotomy as the definition and then proves these two. But they're actually equivalent, right? So as long as you have transitivity, trichotomy and these two are equivalent conditions. I don't really want to prove that because it's boring. Everybody nods it sounds boring. I left it as an exercise, which is a very teacher move. What do my remarks say? Partial orders. So there's a more general kind of order where you don't insist that of two things, one thing is definitely smaller. This is actually a very natural kind of object. If you think about like your food preferences, right? You could say that like you definitely like, let me be an English person. You definitely like tikka masala more than you like beef bourguignon. Definitely. Because we don't like the French. But we love colonialism. But between tikka masala and fish and chips, I don't know. They're both good. And I'm not going to say one of them's better than the other. So that's a partial order, right? I'm not necessarily comparing everything. And a linear order is a special kind of partial order where everything's comparable. You would not believe how much English people love colonialism. You should go and speak to some. They love it. Anyway, they keep doing it all the time. Okay, so linear orders, there aren't really that many of them, especially the finite ones. We can actually draw them. So often we draw them by putting things that are bigger above and then drawing lines between them. So we take this diagram and we turn it on its side. So for instance, if we have this, let's put 3 in there for fun. This is A, and we use the natural less than relation on them that you all are familiar with. We could draw this like this. Right, and because we can draw this picture, that's why we call them linear, because we can arrange them in a line. That's why. Okay, so now we're ready to talk about the natural numbers, all right? Because we have functions, so we can talk about plus and times, and we have this order stuff, so we can talk about like infinite in both directions, which distinguishes us from the naturals. Okay, so we want to build the natural numbers. Get I'm rallying everyone. I was really tired, but I'm getting less tired as we go. Thrilling. Okay, so we want to build something that looks like the natural numbers. Our natural numbers will include 0. I don't want to hear any dissent about that. This is not a democracy. So there are some natural choices. The first historical one was, let's take 0 to be the empty set. That seems easy enough. And then 1 is going to be the set of the empty set. And then 2 is going to be the set of the empty set. And so on. Do you see the pattern? Okay, so this is fine. This was Zermelo's suggestion. But, I mean, it works. You can get everything going. But it has some, there's a better one because it has even more convenient properties. But, I mean, you might notice this has some weird stuff going on. With this version, like 1 is an element of 2. Right? It's like an accidental theorem. And we don't even want 1 is an element of 2 to like be a meaningful question. Right? We'd like that to think that's a type error. It's neither true or false. It's just like nonsense. Because we're dealing with set theory, we have these accidental theorems. All right. So what we want, this is fine, but we're not going to do it. No. Redundant. So what I'd like, the bonus property, is that the set 2 has 2 elements. And the set 3 has 3 elements. And so on. That's what I'd like, for reasons that will become clear later. It's just like a convenient property to have. And also, it would be great if we could, given n, we could build n plus 1 in a very simple way. Right? There's a nice, easy formula to write it down. Okay, and so our plan is that n is the set of smaller natural numbers. That's the plan. And now you might see why it's pretty simple to take 0 to be a natural number, because then this plan works. Right? Because there is one natural number less than 1. Right, 0. There are 2 natural numbers less than 2. 0 and 1. There are no natural numbers less than 0. All right. So if this is our plan, this isn't a definition yet because it's circular, right? Like n is a natural number. If it's a set of smaller natural numbers, it's circular. So what would 0 be? 0 is the set of smaller natural numbers. So what does that have to be intuitively? So what natural numbers smaller than 0 are there? None, right? There aren't any. So this set has no elements, right? So 0 is going to be the empty set, okay? As before. Right, so 0 has 0 elements. What's 1 going to be? So it's a set of smaller natural numbers. You have to list the smaller natural numbers. It's just the set containing the empty set, right? Because that is the set containing 0 via our plan. Right? And then 2. Right, so 1 and 2 look the same as the thing we're not doing. But 2 is where it's different. So 2 is the set containing 0 and 1. Which, if you write it out in terms of the set brackets and the empty set, looks like this. Okay, so and then keep going, and n is the set of 0, 1, up to n minus 1. That's what the plan says. Okay, so this gives us the n has n elements, right? Count them. But also, it's very easy to build n plus 1 if you already have n. Get out of here, proposition. Right, because n plus 1 is a set of all smaller natural numbers, so that's 0 through n, right? It's 0 through n. But the first n minus 1 of those, right, is already n, right? So this, intuitively, is going to be 0 up to n. And that is 0 up to n minus 1 and also n. But that's n union the set containing n, right? Because these two are equal. So you get the next natural number by like adding yourself to yourself as a set, right? Like throwing yourself into yourself as another element. Okay, so this is going to be our plan. This explains why we're going to choose all these definitions. But of course, I can't use these as definitions because they're all circular, right? A natural number is a set containing other natural numbers. So like, what is that? What? How am I going to use that to tell if you're a natural number? Okay, so the plan is to use this operation, like add yourself into yourself, as a starting point. Okay, so given a set X, the successor, X to the power plus, or superscript plus, is X union set containing X. Okay? So successor just says add yourself into everything you had so far. All right, so this is an operation on all sets, right? Like power set or whatever. So one thing that you might try to define the natural numbers would be as follows. The empty set is a natural number, right? That's 0. If n is a natural number, then n, the successor of n is a natural number, and nothing else, right? And nothing else. And is that and nothing else thing that makes that plan fail? Because it's kind of circular again, right? You're relying on already knowing what the answer is in the definition. Like how do you, we need something that's actually like set theoretic that will exclude stuff that we don't want from being a natural number. Here's a little question now. Page 2, question. Which of the following are natural numbers? So I've got 4 sets there. This is according to our plan, still on the level of intuition. Let me scroll down. Oh, people who are watching in the video. It's going to be real weird when they come back on next Thursday for quiz. So which of those are natural numbers, do you think? What's amusing is I actually typoed the question, so I didn't. One of these sets is not the set I meant, but the question is still meaningful. So. So what do we think? Got a head shake? All right, so is A a natural number? No, right? Because it's missing 1. Right? If it had 1 in it, it would be 4. But it doesn't. What about B? Also no, right? It's missing 3. That 4 was supposed to be a 3, so the answer to that one was supposed to be yes, but here we are. It was a turbulent plane ride, so my finger slipped. What about C? No, it doesn't contain 0. What about D? D is the funny one, right? Should that be a natural number? So we don't want that one to be a natural number, because that's infinite, right? That's the set of natural numbers, right? So we need to somehow exclude, this is the set of all smaller natural numbers, right? Smaller than infinity. So we need to be careful about our notion of how we apply this heuristic of the set of all smaller things. Yeah, so that we want that to be the set of natural numbers, which should not itself be a natural number, because then it would be in itself, and it's not impossible, but it's irritating. Okay, so the answer is none, but I meant it to be just B, but here we are. Now I have to edit my solutions and re-upload them. Very embarrassing. Okay, so what we want to do is basically end up with D being the natural numbers, sort of obviously, right? So I want a way of excluding everything that I cannot build from 0 by applying the successor repeatedly. Right, so I only want 0 and the successor of 0 and the successor of the successor of 0 and everything else. Okay, so firstly, let's define what it means to be inductive, which is a first step to that. So, how are we doing on time? Okay. Do I have you till 15 or till 10? All right, easy game. I is inductive if, okay, so number 1. The empty set needs to be an I. That's step 1. Number 2, if something is an I, then its successor is an I. Okay? So question says, let's list some elements that are in an inductive set. Okay, so what's something that's definitely in an inductive set? The empty set, right? Requirement. Now I know the empty set's in an inductive set. What else do I know? The successor of the empty set, right? Like if something's in the set, then its successor is. Which I'll just write as successor because it's easier than writing set brackets. Okay, and now the successor of the empty set is in I. So what else is in I? Successor of successor. And so on, right? Right, so an inductive set is going to contain all of the things that we want to be natural numbers, right? And maybe some extra stuff. And if it contains some extra stuff, it also has to contain that stuff's successor and that stuff's double successor and so on. Okay, but an inductive set is going to have all of our natural numbers in it. Question is, can we build an inductive set? No. Why? Because it's infinite. And the axioms I have given you so far do not allow you to produce an infinite set. Let's be very precise. They don't allow you to prove the existence of an infinite set. You can reason about them, and your reasoning will be true, but you just won't know that you're reasoning about anything. Okay? So the axiom of infinity which has the most pretentious name of all the axioms, it just declares that an inductive set exists. Okay, so the axiom of infinity doesn't just say an infinite set exists, it says an infinite set of this kind exists, which is actually stronger. So now, our plan, which we will not do because it's time to leave, is that the natural numbers is going to be the intersection of all inductive sets. Because every natural number is in every inductive set, right? Because here they are, right? This is going to be 0, this is going to be 1, this is going to be 2, this is going to be 3. So if I just intersect all of them, I should cut out all of the junk, right? And I'll end up with just these. That's the plan, okay? And that's going to be our natural numbers. Okay? All right, so we'll leave that to our next class. Hey, thrilling. I hate exams, y'all. I'm sorry about next Thursday. Mickey makes me give you exams. Blame her. And if anybody wants to admit that they were the person who said that this class was going to be easy and therefore retract their slanderous observations, then I won't give you an F, I promise. Well, that it's yes, indeed. The converse is actually false, and that's why I'm allowed to say that. Yes.
I was just looking at
Exchange all the natural numbers, but like sometimes you build the natural numbers and then throw in anything else and then throw it in. Double that will also be
I don't know my schedule, like by heart. I have a call.
that's the and not the
Yeah, but
other.
it's online because this guy.
So it is, an ordinal is a transitive set that is well ordered by the left.
I hope it's recorded.
You're building the order.
Thank you.
So,
Yeah.
Oh my god, he's on it. I got sad I had to put it up there.
so the idea is to take any inductive set, right? It can't be everything because there is a universal set. Just take something not in your inductive set, then throw that in, and throw in its successor, and throw in its successor. Have another inductive set.
So it doesn't have like all stars when we actually add houses.
Yeah, well, I mean, it's not, we can have this stuff, but you can have other kind of start functions. And then you get like a couple of natural numbers and then a second thing.
Nice.
Yeah.